Hi there. Today we're going to start Chapter 6. It's mostly a algebra review. So there is a lot of algebra in this section. I'm going to go over some of the review material, and then there's a tiny little bit of calculus at the end. So let's get started. All right, so first thing we want to talk about is the definition of a one-to-one function. So this is the definition here. Now there's also something called the horizontal line test that does the same thing, but you have to be able to use this definition. So you basically, if this is true, then the function is one-to-one. We'll see that in the first example. And then you can also use the horizontal line test. So if a horizontal line touches the graph more than once, then it is not one-to-one. So that's a good test to use. It's like the vertical line test with functions, right? But this is a one-to-one function. So here's a few examples. We're just going to go through these. Determine whether each of the following functions is one-to-one on the interval shown. So let's start here with 1 over x. So is 1 over x one-to-one? And essentially, what I don't want you guys to do is just draw graphs and say, well, it fails the horizontal line test or it passes the horizontal line test. I'd really prefer you guys to use the definition. So again, this is the definition. So let's see how to use the definition on part A. All right, so it turns out y equals 1 over x is one-to-one because 1 over a is not equal to 1 over b if a is not equal to b. So what this is saying is that two different numbers can't have the same reciprocal, right? And that's really important because a reciprocal is a special mathematical idea where if you multiply a number by its reciprocal, you get 1. Well, there can only be one number that every other number gets multiplied by. So numbers pair up, reciprocals pair up. All right, what about absolute value of x? So you might be tempted to think of the graph and say, you know what the graph looks like, it's just a V. So you might think, okay, well the graph, it's going to fail the horizontal line test. Sure, but that's true, but let's do it with algebra, right? So it's not one-to-one because the absolute value of -1 is the same as the absolute value of 1, which is 1. So that's using the definition. If you can find two different inputs, A and B, that give you the same output, 1, or whatever it is, then it's not one-to-one. And last one, we just have a table of numbers down there at the bottom. So what do you think? Does that look one-to-one or not? Well, just think about your horizontal line test. If you draw a horizontal line at 10, it's going to hit 2, 10 and 4, 10, which makes it not one-to-one. So, pretty basic stuff. Let's keep moving. All right, now we're going to get into inverses. Again, there's a lot of algebra review here. I'm not going to spend a ton of time in the video reading the definitions. I'll let you guys handle that. I'm just going to get to the examples, okay? So if you have a function, so f of 1 equals 5. So this function takes 1 and sends it to 5. This function takes 3 and sends it to 7. It takes 8 and sends it to -10. Then what are the inverses? So the inverse just does the opposite. It just goes the other direction. So if f sends 3 to 7, then f inverse sends 7 to 3. And if f of 8 is -10, then f inverse of -10 is 8. And of course, f inverse of 5 is of course 1. Right. Really easy stuff, but the reason I'm going over this is because we need this to do a calculus proof later, and I got to make sure you guys understand it. All right, next thing. I do want to go over a notation issue that gives people trouble. So again, this is an algebra thing, but enough people miss it that I put it in the notes. All right, so the inverse of x to the 5th is the 5th root of x, because when you put f inside f inverse or f inverse inside f, if you compose a function with its own inverse in either order, you should get x back out, right? So the 5th root of x to the 5th is always x. the fifth root of x, and then that whole thing to the power of 5 is also x. Okay, so when we write this inverse, it doesn't mean reciprocal, right? So it does not mean 1 over f. So if you had like f of x equals x to the fifth, right, then the inverse is x to the 1/5. But that's not the same as x to the minus 5, which is 1 over f of x. So 1 over f is the reciprocal, which could be written as the entire quantity to the minus 1, but if the minus 1 is next to the f, it means inverse. People do mix that up. Just be careful. All right, so the way we find inverses is you write y equals the function, switch x and y, and solve for y. So let's do a couple of these. So here's the two functions we're going to find the inverses of. You have some more on the homework, but there's just a couple, just to give you guys the idea. All right, so first thing you do is you write y equals your function, switch x and y, then solve for y, right? So subtract 1 from both sides, take the third root of both sides, and you're done, right? Make sure you check your answer first. So the way to check your answer is these cancellation equations. Just take one of the functions and put it inside the other, okay? So here I'm putting the inverse inside f of x, right? So you get the cube root of x minus 1 cubed, right? So the cubes cancel, and then the 1's cancel. So that means that is the answer. So always check your answers on these. That's the only one I'm going to show the checking, because the algebra can get pretty ugly, but you guys get the idea. And I'm sure you guys have all done this in an algebra class. Next one. So here we have a rational function. So switch x and y. Now to solve for y, we have two y's, and we have to turn two y's into 1. So there's really only one way to do this. Multiply both sides by 2y plus 6. Distribute. Get the y's together, so bring 3y to the left side and bring 6x to the right side. Factor out y and divide by whatever's left over. And that's your answer. So I'm not checking the answer on this one. I'll let you guys try that. But that's how you do that one. Okay, moving on. So graphing inverse functions. So switching x and y also gives us the method for obtaining the graph of f inverse from the graph of f. So here, this is just a visualization. There's more of these coming, as you'll see. So since f of a equals b, if and only if f inverse of b equals a, the point AB is on the graph of f, if and only if the point BA is on the graph of f inverse. So that's really important, okay? Because that's what we're going to use to do our calculus stuff here in a second. Here's a theorem. I'm not proving this theorem because it's actually not a horrible proof, but you don't have to know how to prove it. So if f is 1 to 1 and continuous, then the inverse is also continuous, right? And that should make sense, right? Continuity doesn't change just because you switch x and y. Okay, so here's what we're going to do. We're going to do some calculus. So one interesting thing about what we're about to do is that we're going to be able to find the derivative of a function that we can't find the equation of. Okay, so that's really, really interesting. Well, we're going to find the derivative at a point, I should say. So there are functions that have inverses, but you can't write the inverse in a nice way, right? Like if your function is x minus sine x, you can't write that as, you can't write the inverse as just y equals something. It just doesn't exist. But we can find derivatives at points. So what's going on here is that if f is differentiable everywhere, then the inverse is also differentiable, right? Because it's continuous. right? And the only place that the inverse might not be differentiable is where the original function is 0. The derivative of the original function is 0. So think about why that might be true. So the slope capital L of the tangent line of the inverse at AB, so here's our inverse function. Here's the slope, right? So the slope of this is delta y over delta x. But the inverse, all x's and y's switch. So remember, the inverse of f inverse is just f. So the slope L here at BA, so right, if AB is on the inverse, then BA is on the function, is delta x over delta y. So what we're going to do, so the slope of L is the reciprocal of the slope of little l, right? It's 1 over, because you're just switching all the x's and y's. So that means that the inverse, so like the derivative of the inverse of A, so that's delta y over delta x, right? That's what we saw here, right? Is going to be 1 over the derivative of the original function, right? And that should make sense, right? So if you go look at the graph, that should make sense. So the slope of this line is 1 over the slope of this line. Great. Should totally make sense because we're switching x and y. And we know that B is f inverse of A, right, from the graph, right? So this is f inverse of A is B. It's just its own function, right? So that gives us a theorem. So I'm going to prove the theorem. You should know this proof. It helps you understand what the theorem says too. And even though you don't have to do proofs of theorems on a test, it's definitely helpful to understand the proof so you know why you need this theorem. So if f is differentiable with inverse f inverse, and the composition is not 0, right, because you can't divide by 0, then the inverse derivative, so the derivative of the inverse at A, is 1 over the derivative of the function evaluated at the inverse at A. So that's pretty interesting, right? So just think about it. Because here's the thing, we can find this without finding f inverse as a function. We just have to be able to evaluate it at a single point. And we'll see how to do that when we do the example. And this is a general formula. Everything you guys have to do on a homework or a test will look like this. But I mean, A is allowed to be any number in the domain. But to do the proof, we need this version. So let's do the proof. All right, so the derivative of the inverse of A, so here we're just using the limit definition of the derivative, right? So we're just saying that, you know, it's the f of x minus f of a over x minus a. It's the version we had in section 2.1. But if our function is just an inverse, then you just write it with an inverse. Then what we do is we make sure that we label all the points. So this is the same stuff that was the graph, right? So remember, f inverse of a was b on our graph a couple slides ago. That means f of b equals a. So we've got that. Then what we're going to do is we're going to say, let's the inverse of x be y, so that any x value we plug in, we get y. That means that f of y equals x. So a and b are fixed. Those are numbers. X and y are variables. And that's the way this limit works, right? X gets closer to a. Because f is differentiable, it's continuous, so the inverse is continuous. So we're using theorem 6.16 for that. All right, so if x approaches a, which is our limit, then f inverse of x approaches f inverse of a, right? Because of continuity, right? And what we can do is we can just say that y approaches b, right? Because f inverse of x is y, f inverse of a is b, right? Here's a, f inverse of a is b, f inverse of x is y. And then what we do is we're just going to rebuild this equation. So here's the same thing at the top. We're just going to replace everything with its y and b equivalent. But what does it do? Because it's an inverse function, it switches. It's like upside down looking, right? So look, if x gets closer to a, y gets closer to b, we knew that. But it's upside down, so how do we fix that? Well, you just write it as 1 over the reciprocal. Then you move the limit inside. All right, if the limit exists, you're allowed to move the limit inside. Well, this is just the derivative evaluated at b. That's what this is. Right? This is just this guy, but evaluated at b, right? And that's it. So that's our proof. All right, let's keep moving. And then what we do is we replace b with what we named it up here, which is f inverse of a. So there you go. So it's 1 over f prime f inverse of a. All right, so let's use this to do a homework problem. All right, so look at what it's saying. If we have a function, find the derivative of the inverse at the point -2. You don't learn how to find the inverse of a function like this. It can be done, it's just horrible. But we don't need to, we can use the theorem. Right, so f inverse prime of -2 is 1 over f prime of f inverse of -2. So I'm just replacing the a with its value, right? Because it says, that's what it is. Okay, so here's our f of x. So we need f prime of x. Now what we do is we say, let's think about what f inverse of -2 is saying. So we're trying to find this quantity on the inside. F inverse of -2 is the value of x for which f of x equals -2. So we're looking for the number that if we plug it in to the original function, we get -2. So you look here and you say, what number plugged in here would give me -2? Well, you can pretty clearly see that plugging in 0 gives you -2. That means that this value is 0. So this whole thing is 0. So we just plug that into the original equation, right? So f prime of f inverse of -2 is just f prime of 0. So we just take this and plug in 0. And we get 1. Now we plug 1 in the original function, right? So f inverse prime of -2 is 1 over, so I'm just replacing this. Well, it's 1 over, this guy was 1. 1 over 1 is 1, and we're done. So the trick on problems like this is that you're going to be given a function, and you have to be able to look at this and say, I need this to be equal to, I don't know, -2, right? So you got to find numbers that if you plug in here, you get -2. And there could be more than one, but you only got to find one. And there's a picture of what it looks like. So here's the original function. Here's the inverse. Notice that this does not pass the horizontal line test. This is not 1-to-1, but it doesn't matter if it's 1-to-1 or not. It just has to be 1-to-1 in a small region around what we're trying to find, and it is. So look at what we were trying to find. We were trying to find, let me go all the way back, sorry. We were trying to find f inverse prime of -2. So let's look at the graph and see what that tells us. So here's f inverse at -2. So there's -2. The x value is 0, which we figured out. What's the slope of this line right here? Well, it's 1. So there's the line y equals x, and there's the line y equals x plus 2. So you can see that the reason I picked this point was just because I wanted to show you that it was parallel to y equals x. And so that's definitely a believable value for the derivative. Well, that's it. Short section today. If you got any questions, go ahead and post on the discussion boards or shoot me an email. And that's it for today, and I'll see you guys next video.